At the farthest edge of our solar system, where sunlight weakens into a pale and distant glow and temperatures fall to levels that challenge imagination, one world has quietly reshaped what we understand about planetary science. Pluto. For decades, it was treated as a frozen remnant of planetary formation, a small and distant body drifting in the icy expanse of the Kuiper belt. Far from the warmth of the sun and beyond the reach of detailed observation, it appeared static and unchanging, a relic preserved from the solar system's earliest era. When Pluto was reclassified as a dwarf planet in 2006, its status in the public imagination seemed to diminish even further. It became, for many, a distant curiosity rather than a world of active geological interest. Yet modern exploration has proven that assumption profoundly incomplete. With the arrival of advanced observational technology, including the extraordinary capabilities of the James Webb Space Telescope, Pluto has been revealed not as a dead ice rock, but as a dynamic and evolving world. Beneath its distant and dim exterior lies a system shaped by motion, chemistry, and hidden energy. Pluto's surface is far more complex than once believed. What was previously thought to be a uniform frozen crust is instead a shifting landscape of nitrogen ice, water ice, and complex organic compounds. Vast plains appear remarkably young in geological terms, suggesting that the surface is being renewed rather than left to decay over time. Towering mountains of water ice rise like frozen monoliths, hard as rock in the extreme cold, while smoother regions suggest slow resurfacing driven by internal processes. One of the most striking discoveries lies in the region known as Sputnik Planitia, a vast basin that has become central to modern interpretations of Pluto's geology. Once assumed to be a simple frozen plain, it is now believed to be a region of slow, convective motion. Nitrogen ice within this basin behaves almost like a geological fluid, slowly rising and sinking in patterns that resemble convection cells. This constant churning reshapes the surface over long timescales, erasing impact craters and renewing the landscape in a continuous cycle. Even more intriguing is the possibility that beneath Pluto's icy crust lies a subsurface ocean of liquid water. Protected by layers of insulating ice and sustained by internal heat generated through radioactive decay, this hidden ocean may have persisted for billions of years. If it exists, it would place Pluto among a small but fascinating group of worlds in the outer solar system that may harbor liquid water beneath frozen surfaces. Such an environment raises profound questions. On Earth, liquid water is inseparable from the chemistry that supports life. In the cold and distant environment of Pluto, any subsurface ocean would exist in darkness, cut off from sunlight, but potentially enriched by chemical compounds delivered from the surface. Organic molecules known as tholins, formed when methane interacts with ultraviolet radiation, coat large portions of Pluto and its moon. These reddish compounds may slowly migrate downward, mixing with subsurface water over immense periods of time. In theory, such interactions could create the basic chemical conditions needed for prebiotic processes. Pluto's atmosphere adds another layer of complexity. Though extremely thin, it is remarkably dynamic. Composed primarily of nitrogen with traces of methane and carbon monoxide, it expands when Pluto moves closer to the Sun in its elongated orbit and collapses again as it moves farther away. This seasonal breathing of the atmosphere creates cycles of frost and gas, as surface ices sublimate and later refreeze, reshaping the upper layers of the planet over time. Haze layers have also been detected extending high above the surface. These hazes, formed by photochemical reactions driven by sunlight, create a soft bluish glow when viewed against backlighting. Despite the weak solar energy at Pluto's distance, these atmospheric structures persist, suggesting complex interactions between radiation and atmospheric chemistry that were not expected for such a small and cold world. Pluto's relationship with its largest moon, Charon, further deepens its mystery. Rather than a typical planet-moon system, Pluto and Charon form a binary pair, orbiting a shared center of mass located in the space between them. This gravitational partnership creates a stable but unusual dynamic, locking both bodies into a synchronized rotation where the same hemispheres always face each other. Tidal interactions between Pluto and Charon likely play a role in shaping their internal evolution. Subtle gravitational flexing may generate heat within their interiors, contributing to the maintenance of subsurface activity. Charon itself shows signs of ancient geological processes, including vast canyons and contrasting surface regions that hint at a more active past than previously assumed. Its surface coloration, marked by reddish tones, is thought to result from material transferred from Pluto's escaping atmosphere, slowly accumulating over time. Far from being a simple ice-covered rock, Pluto is now understood as a system of exchange. Material flows between surface and atmosphere, between Pluto and Charon, and potentially between crust and subsurface ocean. It is a world defined not by stillness but by slow and persistent transformation. Even its interaction with the solar wind has proven unexpected. Despite lacking a strong global magnetic field, Pluto exhibits complex atmospheric escape patterns, where charged particles are stripped away and carried into space. These interactions suggest that the boundary between Pluto and interplanetary space is more active and structured than once believed. The implications of these discoveries extend beyond Pluto itself. The Kuiper Belt, once thought to be a quiet reservoir of inert icy bodies, is increasingly recognized as a region of diverse and evolving worlds. Each new observation reveals variation in composition, internal structure, and geological activity. Pluto has become the most prominent example of this transformation in understanding, but it is likely not unique. What makes Pluto especially compelling is the way it challenges assumptions about scale and activity. Worlds once considered too small and too cold to sustain geological processes are now revealing evidence of internal heat, subsurface oceans, and ongoing surface renewal. The boundary between active and inactive worlds is no longer clear. Pluto stands as a reminder that distance does not imply simplicity. Even at the edge of the solar system, complexity thrives. Ice flows like slow-moving geology, atmospheres breathe in seasonal cycles, and hidden oceans may persist beneath frozen crusts. In the faint light of the distant sun, Pluto continues to evolve. As observational technology improves, future missions may one day return to this distant world, not to find a frozen relic, but to explore a living system of ice, chemistry, and hidden energy. Drilling through its surface or scanning beneath its crust could reveal whether its subsurface ocean exists and whether it has ever been chemically active in ways that resemble the early steps toward life. For now, Pluto remains a world of quiet revelations. It is no longer a forgotten object at the edge of the solar system, but a dynamic environment that continues to challenge long-held assumptions. It reminds us that planetary evolution is not limited to warm or Earth-like conditions, but can unfold even in the coldest and darkest regions imaginable. In the vast architecture of the solar system, Pluto occupies a distant frontier. Yet that frontier is not empty. It is active, layered, and full of subtle motion. And in its slow and frozen rhythms, it tells a larger story about the universe itself. That even in the most remote places, change never truly stops.